Hello, so we are going to start chapter 10. It is the second part of hypothesis testing. So as you learned from chapter 9, the statistical hypothesis testing method is pretty much unique, very unique and different from like estimation and other statistical approaches. So I spent 2 chapters only for statistical hypothesis testing. And this is a continuation of chapter 9. So if you did not finish chapter 9, you will not be able to follow chapter 10. So make sure you finish chapter 9 first before taking this. Okay. So what we learned in chapter 9 is actually pretty simple framework how to implement hypothesis testing. I explained the underlying philosophy, the decision-making philosophy in hypothesis testing, and then we applied the central limit theorem and some statistical techniques. How we can tell or how we can define the how suspicious the observation is given your hypothesis. So you have your own hypothesis, and if it was true, then you can tell if the data is similar to your hypothesis or different. If it's further away from your hypothesis, then your hypothesis is less likely to be true. So we represented that as a p-value, which can be interpreted as the ranking of suspiciousness. So like as the p-value close to approaches to 0%, that means your outcome, your data is very suspicious, or your hypothesis is very suspicious, different from your data. But if the p-value is close to 100%, then it's not suspicious at all. It's at the bottom of the ranking of the suspiciousness. Okay. So and then we learn 3 different decision-making rules, like that can be based on the p-value or t-statistic or the critical values. It depends on how, like it's just a method of algebra, what kind of algebra you are going to use, or which one is more convenient given your data and given your situation. And also it depends on your software, what kind of software you use. They may have different types of method. They may use different types of methods. So I explained all 3 in the previous slide. And today we are going to discuss 2 additional topics like this. One is about the accuracy. Like we only talked about how to make a rejection, how not to make a rejection, but I did not say what is the probability of a correct decision or wrong decision. So in statistics, it's always very important to evaluate your own accuracy, right? Because we have to live with our random errors. So we know there are random errors. So we need to think about the probability of potential errors. So we are going to discuss that in the first half of this chapter. And in the second chapter, we will think about a null hypothesis with inequality. In the previous slide, in the previous chapter, I considered I thought about the hypothesis with equality. If the population mean equals something versus different. But in reality, like we are interested in inequality. Like we believe something is smaller than something or greater than something. So then testing those inequalities may be more useful. That is the second half of this chapter. Okay, let's go. Okay, let me start with the basic setup. So I started the chapter 9 with the presumption of innocence, right? So exactly, let's start from there again. So suppose that a person was charged with a crime, so brought to a criminal trial, and there the null hypothesis is that the defendant, the person who is charged, is innocent, you have to believe that the defendant is innocent if there is not enough evidence, right? Versus the alternative hypothesis is guiltiness. The defendant is actually guilty. There are enough, so you take the alternative only when there is sufficient evidence showing that the defendant is clearly guilty without beyond doubt. Okay. Right. So then, in this case, there are only two possible results. Right. If the null hypothesis is rejected, that means the defendant has to go to prison. Like, if not, if the null hypothesis was not rejected, then the defendant will be set free. Okay, so this is basic, simple yes or no decision, but the result may be different from the truth, right? The truth can be either innocence or guiltiness, right? So H0, the null hypothesis could be true, right? The defendant is actually innocent, or actually the truth is the alternative, like the null hypothesis could be wrong, so the defendant is actually guilty. But even though the defendant is guilty, there may be no evidence, or vice versa. Even though the defendant is innocent, there may be some kind of manipulated evidence, which is believed to be like strong evidence, right? So, a judge can make a wrong decision. That is possible, right? And then it is easy to define an error, like if the condition is that the defendant was actually innocent, then if the decision was to send him to jail, that is an error, right? But if the defendant was set free, that is correct, right? But if you change the assumption, if like assumption about the truth, if the defendant was actually guilty, then a wrong choice is when you set him free. That is an error. But if you send him to jail, that is the correct decision. So when we think, because in hypothesis testing, the result is the decision is either yes or no, like rejection or not. So so there are two different types of errors depending on the actual truth. By the way, the truth is never known. We never observe the actual truth, but like theoretically, we can just assume that we can condition on the truth, and we can think about two different errors. And as you can see, in this case, sending a jail is error, but in the other case, that is correct. But setting free is an error. So what is the correct, what is right, and what is wrong depends on what is the truth. So there are two different types of errors. So in the general setup, we call them like this way. If the null hypothesis was true, then we should not reject the null hypothesis. In that case, rejection is an error. We usually call this a type 1 error or alpha error. I really hate this name. Like, it's type 1 and type 2. There is no reason to call this type 1. But like different textbooks use like different names. But I think type 1 error is more common terminology. So I will use type 1 error as the term for this error, right? But in this case, so if the null hypothesis was true, rejection is a type 1 error, but non-rejection is correct. But the other case, if the null hypothesis was actually wrong, then rejection is correct, right? You have to reject a wrong hypothesis. That is correct, but non-rejection is another type of error, which we call type 2 or beta error, right? So I will call them from now on type 1 or type 2 error, but some textbooks use alpha error or beta error, right? So let's think about this then. How can we analyze it? So like, remember, like, so suppose that we believe that the true mean is here. That is our null hypothesis. So we believe the true mean is here. And then we said we believe that the outcome is more suspicious if it is somewhere outside, far from the hypothesis. So further from the hypothesis, the more suspicious, obviously, right? So based on this idea, we are going to reject the null hypothesis if the data, the sample average, lies here, right? Somewhere here, right? So we are going to reject realized outcomes, like if the outcomes are outside, right, far from the hypothesis. So rejection region is the tails, outside tails, okay? But do you know the outside tails can happen? Like, so we call them lower critical value and upper critical value. We set up critical values, and outside those critical values are rejection region, right? We are going to reject outside the critical values, and then, oh, but we know that the sample average is distributed according to a normal distribution. When the hypothesis is correct, the center of the normal distribution would be mu0, your hypothesis, right? The value you are assuming, right? So it will be a normal distribution centered around mu0, your belief. But the problem is, even though the center is correctly mu0, there is some probability that the sample average takes the rejection region, right? So it is possible that the sample average can take a value that is too different from mu0, from the center, even though the center is correct. Then that's when you have a type 1 error, right? Even if mu0 is correct center, but there is a possibility you observe this thing or this thing, then you have to reject it, because what you only observe is just one point, one realization, not the whole distribution. So there is no way. So this bell curve is only in our theory, like it's our kind of only in our theoretical analysis, but you never observed this bell curve or the distribution in real data analysis. So you have to reject it if the data is far from the hypothesis. Okay, that is type 1 error. But now suppose the null hypothesis is wrong. So then the actual center of the normal distribution is somewhere deviates from your hypothesis. So you believe the center is mu0, but actually it could be mu1, right? Suppose that the center is not correct. In that case, your sample average will be generated from a normal distribution that is like misaligned. It's not exactly what you imagined, right? Right, so your normal distribution is shifted to mu1, has a center at here. In this case, so now the null hypothesis is wrong. So you have to reject it, right? You have to reject it. Rejection is the correct decision in this case. But you fail to reject it if the realization, the sample average is close enough, like is within the critical values. If the sample average, realized sample average is within the critical values, you cannot reject the null hypothesis, then that is another error, right? So the center is actually not mu0, but it is possible that the sample average is generated in between the critical values. Then you cannot reject the null hypothesis, so that is a type 2 error. This is, again, the theoretical analysis. We can imagine depending on what is the truth. Okay, so what we are going to do in the first half of this chapter is to calculate this probability. The area here is the probability of type 2 error when the truth was actually mu1, right? So, and similarly, we can calculate type 1 error probability, which is these tail probabilities. So it is a little confusing because you have to think about your hypothesis and the truth separately, right? Your hypothesis and so you have your own hypothesis and you have your own data and there is truth separately. All these three things are separate things, but we will consider them at the same time. So it can be a little bit confusing, but actually there is no additional techniques. We are going to apply the same normal distribution, then it should be clear. And the result is actually pretty clear. Okay, thank you for watching. I will continue with a numerical example in the next video. See you there. Bye.